Hello everyone. The purpose of this video is to provide a brief overview of SchedulePro's probabilistic modeling and variability analysis capabilities, which allow users to efficiently analyze many potential outcomes of a production plan, rather than using deterministic or fixed durations for every operation. Variability is an inherent aspect of manufacturing processes. Common sources of operational variability include differences in skills of operators, availability of operators at a specific point in time, conflicts in use of equipment units that are shared by multiple operations, unexpected equipment failures, etc. Despite these production variabilities, standard deterministic process simulations do not account for random variation in input variables. Instead, they provide results associated with one specific situation, often considered to be the expected scenario. This can create problems when attempting to determine a facility's production capacity and its potential bottlenecks, because different resource conflicts may arise depending on the timing and duration of various operations. In other words, a production plan that is feasible under one set of conditions may become infeasible or much less efficient when it is simulated with a different set of conditions. Furthermore, the full range of possible scheduling outcomes is not apparent when only a single model with fixed input parameters is simulated. To address these issues, SchedulePro's variability analysis capabilities allow users to build probability distributions into their operation durations in order to easily perform simulations with different input conditions. The first step in this process is to add a new operation duration variable. In this simple example, I will add a new variability parameter for the ferment operation in procedure P5 of the Protein 1 recipe. Under the distribution menu, I can choose from a variety of probability distribution options. For instance, triangular distributions are often used when there is limited data to determine the underlying distribution. In this case, I'll select a triangular distribution with values of 40, 64, and 48 to represent the assumed minimum, maximum, and highest frequency values. Many different operations within a given recipe could be given variable durations if desired. Variable durations may also be specified for operations in many different recipes. In this example, a variable duration based on a normal distribution has already been assigned to the ferment operation in the Protein 2 recipe. Note that this example does not attempt to account for variability in all possible operations. Instead, the fermentation operations were given variable durations because the production fermenters are the bottlenecks in these recipes. Therefore, changes in their durations can have a substantial impact on the overall schedule, whereas changes in durations of other units may have little or no effect on plant throughput due to their substantial idle times. In general, variability analysis should focus on the variables which are most likely to have a large impact on the process. Note that when the production plan is scheduled, the default expected value of each duration is used initially. Here you can see the consistent durations for the ferment operations in both recipes. Note that each campaign in this example was given some slack time between consecutive batches in order to accommodate small delays which may occur during a given batch. Next, the impact of operation variability can be studied by clicking the Play Simulation button. When this button is clicked, a single potential outcome of the schedule will be simulated by selecting variable durations for operations which have been assigned probability distributions. The moving red line represents a current timeline that steps forward as the simulation proceeds. Notice that the individual fermentation durations change as the current timeline progresses and coincides with them. In some cases, conflicts are created when an overlap occurs between multiple operations which need to use the same equipment unit. Those conflicts may optionally be automatically resolved by SchedulePro. The time step and the speed of this simulation may be modified by clicking the Simulation Settings button. In this case, the simulation is set to step forward in 12-hour increments every half second. Note that you may return to your original schedule by clicking the Undo button here if desired. You can also redo previously undone changes by clicking this button. The Undo and Redo buttons also apply to other types of changes to the schedule, such as manual changes to operation durations or equipment assignments. The Play Simulation button could be clicked again to view another possible outcome of the schedule, but a faster way to run a new simulation is to simply click the Randomize Schedule button. When this button is clicked, SchedulePro selects a new set of values for the variable duration operations. This feature allows you to quickly view multiple potential scheduling outcomes. Notice that in some cases, a longer than normal operation creates a conflict that may be resolved by selecting an alternative equipment unit for that procedure, if an alternative unit is available, rather than by delaying a subsequent batch. For example, the second batch of the Protein 2 campaign has been switched to unit R2 on line 2, rather than unit R1. This allows the second batch to be scheduled at its originally planned time, even though unit R1 is not available yet. In addition to exploring the impact of variability on equipment utilization and scheduling, changes in other resources, such as labor, heat transfer agents, etc., may be visualized. This allows potential bottlenecks in the facility's supporting systems to be identified. For instance, here you can see the inventory level within the purified water, or WIFI, system at different points in time. In this model, the WIFI storage tank has been given a capacity of 30,000 kilograms, and additional WIFI is produced at a rate of 2,500 kilograms per hour whenever the level in the storage tank goes below 50% of the tank's capacity. Based on these specifications, the WIFI supply system can usually meet the demands of the process. However, under certain scenarios, such as this one, the WIFI system cannot keep up with the processing demands, and production may need to be delayed in order to prevent the WIFI storage tank from running dry. In other words, a WIFI supply system that is built based only on a single static schedule using nominal production values may not be able to meet the maximum WIFI demand that is likely to occur under other operating scenarios. SchedulePro allows you to view the impact of schedule variability on resources such as the purified water system, heat transfer systems, etc., and size them based upon maximum demand scenarios rather than just a typical scenario. Note that SchedulePro also has the capability to shift the timing of certain operations in order to keep a given resource within user-defined limits that have been set for it. Finally, statistics related to a large number of simulations may be calculated by using the Variability Analysis feature. In this case, 200 trials will be simulated with fermentation durations selected from the probability distributions defined earlier. Note that the number of trials required for a thorough variability analysis is a function of the number of random variables in the production plan, which is based on the number of defined variables in each scheduled recipe times its number of batches. In other words, a production plan containing many variables will require many more trials to produce ample results compared to a production plan with only 1 or 2 variables and a few batches. The result of the Monte Carlo simulation, which is performed based on the variability settings, illustrates the expected range of scheduling results with respect to key process parameters, as well as the relative likelihood of various outcomes. Here you can see key statistics related to the range of schedule durations, as well as a histogram of the makespan results. The sliders above the histogram allow you to determine the probability of completing the schedule within certain limits. For instance, based on the assumed distributions specified in this model, if you would like to be over 90% confident that you will be able to complete the production plan on time, you should allocate 493 hours. Note that the duration values chosen for each simulation and the makespan results for all of the trials are recorded by SchedulePro. These data may be exported for additional analysis within an application such as Microsoft Excel. Also note that the nominal makespan for this set of trials is about 486 hours, whereas the maximum makespan is 500 hours. In other words, basing production plans on the nominal or expected operation durations may result in missed deadlines. This concludes the variability analysis video. In summary, SchedulePro allows users to incorporate variability into their scheduling models in order to easily see a range of possible scheduling results and to identify specific conflicts that may be created due to infrequent or unexpected overlapping in resource usage. These analyses are useful for facility design, throughput analysis, and debottlenecking. By accounting for variability, you can also determine realistic throughput values and effectively plan facility and labor resource allocations. For additional details on building models in SchedulePro, please refer to the SchedulePro manual and the SchedulePro example files. Note that the example files are included with the free SchedulePro evaluation version, as well as the full SchedulePro application. Please also refer to the other online training videos located here.